the normal shock waves. A common irreversibility occurring in supersonic internal or external flows in the normal shock wave sketched in this picture, except at the near vacuum pressure. Such shock waves are very thin, for micrometer thin. So the thin, macro, and approximate a discontinuous change in flow properties. We select a control volume just before and after the wave as this picture. The analysis is identical to previous description. A shock wave is fixed strong pressure wave. The compute all properties change rather than just the wave speed. We use all our basic one-dimensional steady flow relation for the flow from 1 to the upstream and section 2 downstream, as shown also in this picture, downstream, upstream, and downstream. Continuity equations. In the compressible flows, we have continuity equations, momentum, energy, and the equation of state. The continuity say that for the 2.1 and 2, we should have rho 1, V1 equals to rho 2, V2, and is constant. The momentum equation is P1 minus P2 rho 2 V2 square minus rho 1 V1 square, and energy equation H1 plus 1 second of V1 square, and the potential energy is negligible. Constant, and perfect gas. Relation is R is rho 1 T1 P2 rho 2 T2. We have also a relation for isentropic coefficient, constant Cp. H equals to, and K constant, Cp on Cv. Note that we have cancelled out the areas, which is justified even in a variable dissection because of the thinness of the wave. The first successful analysis of these normal shock wave relations are created by ranking. If we assume that the upstream conditions are known, for example, if I assume that upstream point 1, T1, V1, H1, and T1 are known, two solutions are found, and the correct one is determined from the second law of thermodynamics, which requires that S second greater than S1, we have a increasing in entropy. So we can write the velocities V1 and V2 can be eliminated to obtain the Rankine relation. Rankine Harmoniot relation V1 and V2 negligible. That not negligible can be eliminated because it's approximately same and vanishes. So we have this relation H2 minus H1 1/2 of P2 minus P1 1 on this contains only thermodynamics properties and is independent of the equation of state. Introducing the perfect gas law, we write car P on we can rewrite this equation as for the 2-point densities where beta we can compare these with the isentropic flow relation for a very weak pressure wave in a perfect gas as this relation for a very weak we had before for a very weak pressure wave in a perfect gas. Also, the actual change in entropy across the shock can be computed from the perfect gas relation, which is, let me write the actual entropy change. In across the shock. Assuming a given wave strength, for example, if we can compute the density ratio and the entropy change and list them as a table for K equals to now for air. Anyway, Mach number relations is the next description. For a perfect gas, all the property ratios across the normal shock are unique function of K and the upstream Mach number. Let me write. For a perfect gas, all the properties ratios across the normal shock are unique functions of K and the upstream Mach number at 1 upstream. For example, if we eliminated simplify the relation, we can obtain the relation for the pressure on the upstream and downstream of the shock wave at the relation of K. So P but for a perfect gas, we had also this relation. The perfect gas, we have O1 V1 square on P1, O1 V1 square on P1 equals to K V1 square on K RT T1, which is equals to the K square. Now we can rewrite the equation as below. From this equation, we see that for any car, P increases as the shock occurs only if Mach at upstream is greater than 1. Thus, for the flow through a normal shock wave, the upstream Mach number must be supersonic shock wave. the Mach number are supersonic to satisfy the second law of thermodynamics. But we can also calculate the Mach number for the downstream Mach number. In shock waves, P Now we can calculate the Mach number at point 2. Since Mach 1 must be supersonic, this equation predicts for all greater than 1 that the second Mach number must be subsonic. Thus, a normal shock wave decelerates a flow on mass discontinuity from supersonic to subsonic condition. We can also calculate the properties of the flow as a function of Mach number of upstream. We can write the other properties of the downstream shock wave in the function of Mach number of upstream. The first relation is for density. S2 plus 2, which is also equals to the velocity ratios, the temperatures, square for the stagnations densities of the shock wave now also relation which is a function of specific ratio and Mach number. Of additional interest in the fact that the critical or sonic truth area in the shock wave, the critical or sonic truth area in a duct increases across a normal shock. One second. The next section is about let me summarize the shock wave as follows. Shock wave properties or specification. The upstream flow should be supersonic, and the downstream is the second one. For perfect gases, rarefaction shocks are impossible. And only a compression shock can be exist. Three, the entropy increases across the shock. With consequent decrease in stagnation pressure and stagnation density, and an increase with consequent decrease in stagnation pressure P0, stagnation density rho 0, and increase in the effective sonic area. Area for weak shock waves are very nearly isentropic. The next section is about the operation of converging and diverging noise.